Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is a little mini-series within that playlist. And this mini-series deals with two-factor factorial designs with interaction. This is part 2 of an 8-part series. And we're looking at the column space of the design matrix. So as a reminder, the model is y equals x star beta star plus epsilon. So it is a linear model. And we break the design matrix into parts. So one associated with the grand mean, factor A, factor B, the interaction between A and B, and of course plus epsilon. Where epsilon is normally distributed, mean vector 0, covariance matrix sigma squared. Now we're going to look at the column spaces of each of these respectively. So let J, defined like this, be the column space or the perpendicular projection matrix onto the column space of 1s. And then this J times Y creates a grand mean vector, which is the sample mean, grand mean, times the 1 vector. We just generically call it YGM bar. Let M alpha, defined like this, be the perpendicular projection matrix on the column space of X alpha. And M alpha, this perpendicular projection matrix, pre-multiplying it Y by it, creates the mean vector for treatment A or factor A. And I'm going to point you back to the previous mini-series for this detail. Now the previous mini-series is two-factor factorial designs without interaction. But there's a lot of similar development. So in the interest of time, I'm going to point you back to that mini-series. Now, since the column space of 1 is a subspace of the column space of X alpha, the difference of the perpendicular projection matrices creates another perpendicular projection matrix onto the orthogonal complement space of the column space of 1 with respect to the column space of X alpha. And what that means is if you pre-multiply any dangling vector by M alpha minus J, it shoves it into the column space of X alpha orthogonal to the column space of 1. Now let M beta, defined like this, be the perpendicular projection matrix on the column space of X beta. M beta times Y is equal to the treatment B, factor B mean vector. And I'm going to point you back to the previous mini-series. And since 1, the column space of 1 is a subspace of the column space of X beta, the difference of their perpendicular projection matrix is a perpendicular projection matrix onto the orthogonal complement of the column space of 1 with respect to X beta. Now let's let M alpha plus M beta minus J be the perpendicular projection matrix onto this entire column space. And I'm going to point you back to the previous mini-series for detail of that. Now let M, now this is new because we haven't dealt with the interaction term in two-factor factorial designs. Let M alpha beta be defined like this, and it's the perpendicular projection matrix on the column space of X alpha beta, so the interaction space. Now let M be the perpendicular projection matrix onto the entire design matrix, and it's defined like this. But here we have to use a generalized inverse because this is it's a singular matrix. Here in what we've done previously, we can use the inverse because they're invertible matrices. Now, but since the column space of X star is equal to the column space of X alpha beta, and perpendicular projection matrices are unique onto a column space, that says M is equal to M alpha beta. Now note that this column space of 1 X alpha X beta is a subspace of the column space of X alpha beta. So that means the difference of their two perpendicular projection matrices creates a perpendicular projection matrix onto the orthogonal complement of this space with respect to X alpha beta. Okay, so now we're going to look at this perpendicular projection matrix, or the M alpha beta times Y. Now we looked at this in previous videos, but we haven't yet, so I'm going to develop it a little bit here. Now, the first thing we want to do is look what this looks like, and then what the product of these two look like. So X alpha beta transpose times X alpha beta creates an identity matrix times n. And then if you take the inverse of this, you just take 1 over n times that identity matrix. And if you look at X alpha beta times X alpha beta transpose, it creates a block diagonal matrix of UN. Now UN is a square matrix of all ones of size n. Now, so that means M alpha beta, the perpendicular projection matrix on the column space of X beta, defined like this, is actually a block diagonal matrix of 1 over n. So when we take this M alpha beta times Y, it creates A times B little chunks of constant vectors. So the first one is the sample mean of cell 1, 1. So that's level 1 of A and level 1 of B. It's the sample mean, and of course times the mean vector 1. So it's repeated n times. The next cell is the sample mean of 1, 2. Repeated n times, and it just keeps going through all A, B levels, and we generically call it Y alpha beta bar, or the mean of the interaction, of alpha and beta. Now this what we've done decomposes the column space of X star into 4 orthogonal spaces. So the column space of X star can be thought of as this. So it's a column space of 1 X alpha star X beta star X alpha beta star. And I'm going to point you back to the previous mini-series where we reused the Graham-Smith algorithm to create this. So note that the column space of 1 X alpha is equal to the column space of 1 times X alpha star, where these two column spaces are orthogonal. Now if we look at the column space of 1 X beta, that's equal to the column space of 1 X beta star, where we use the Graham-Smith theory, Graham-Smith algorithm to make these columns orthogonal to 1. And then we kind of got by default that it's also orthogonal to X alpha star. Now the entire column space is equal to this column space, where we've made them all orthogonal to each other. Now next, I'm gonna point you back to a video I have in, I think, the matrix playlist called Sum of Perpendicular Projection Matrices. So if we have a column space and they're all orthogonal, then the perpendicular projection matrix onto that entire column space is the sum of the perpendicular projection matrices. So M, which is the perpendicular projection matrix onto this entire column space, it's going to be J, M alpha minus J, M beta minus J, and then this one was M alpha beta minus M alpha plus M beta minus J. But when you write this out, so this J cancels with that comes down, M beta comes down, the minus J comes down, this, and then you distribute the J, cancel, everything cancels but M alpha beta. And that's what we actually were saying earlier, that those two perpendicular projection matrices were the same matrix, or the same perpendicular projection matrix. Okay, well that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like it and subscribe so you don't miss the next one. Thanks. Bye.